Hello and welcome to another edition of DDI's Productivity Webcast. I'll be your host, Joseph Richter, and we've got a lot to get through today, so let's get moving. Okay, the first item that we'll go ahead and talk about will be the assembly features and the assembly structure, being able to reorder the tree and so on. Along with that, I'll share some mate tips and tricks that will help you assemble your assemblies quicker. In addition to this, we'll discuss component patterns and the options that are available to us for this. I'll also share with you using assemblies to gather information more than just will these parts go together. We'll talk about using simplified configurations, including the easy button. That's right, a nice automatic tool that will help us create simplified configurations to help those large assemblies actually function on less than stellar equipment. And finally, we'll round it out with best practices. So with that, we'll get started. Alright, first up, assembly features and the assembly structure. The features that we can perform at the assembly level are cuts, cut revolves, or cut extrudes. When doing these cuts, we do have the added ability to specify which components will be impacted by that cut. This is referred to as the feature scope. We also have special type of cuts. That is the hole wizard. I'm sure you're all familiar with it. Well, at the assembly, we also have a feature called the hole series. The difference between the two is the hole wizard cut exists only at the assembly level, just like the cut revolve and the cut extrudes would. The situation where you would use the hole wizard at the assembly level would be for a match drill type of situation. That is where you have mating pairs that are one-ofs, one-of-a-kinds, items that you cannot locate until they are physically put together and you physically drill them at the assembly level. However, that's not going to be most situations. Most situations are you have a stack of parts, you know how they go together, you know where they're going to be bolted together, and rather than trying to go into each part, put the holes in the same locations in each part, it would be nice to take advantage of that assembly, mate the parts together, then punch the holes through them and have that hole go back to the part level. This is referred to as the hole series, so this will do all of that for you. The nice thing about this, it does create an in-context feature, so that way if you change anything in the assembly, this hole series will update those parts. Next, I want to talk about modifying the assembly structure. Sometimes when you start making an assembly, sometimes we don't plan things out very well, and as a result, we later on figure out, oh, maybe these parts would be better as a sub-assembly because I'm winding up using this group of parts in multiple locations. But not all is lost. We can create new sub-assemblies right inside that assembly. We also have the ability to say, you know what, these parts really should not be a sub-assembly. I want these at the top level. We can dissolve sub-assemblies and pull those parts back into the top level assembly. Or maybe you want to move parts in and out of sub-assemblies. We call this promoting and demoting parts. So we can change the assembly structure that way. And finally, if you are moving parts in the tree, and this is, as a best practice, you want to order your tree alpha or numerical based on the part names or part descriptions. When dragging parts below sub-assemblies, SOLIDWORKS thinks you're trying to demote that part into that sub-assembly. So the way that we can tell SOLIDWORKS, no, I want this part right below the sub-assembly, is to use the Alt key. So push and hold Alt lets you reorder those parts. So I'll take us into SOLIDWORKS and show some of this. Okay, the first assembly I'm going to open is called Feature Scope, and I'm going to go ahead and insert an assembly feature. Going to be a cut extrude. And what I want to set up here is maybe a partial cutaway for use in a drawing view to show all the internal components. So as I do a cut through all and just hit OK, as expected it cuts through all the parts, including the internal parts. But the whole purpose of this cutaway is to show these internal parts. So I'm going to go ahead and edit the feature, and here I'll talk about section scope. As I was describing before, these are the components that will be impacted by the cut. So as I select these three here and hit OK, I can see that those internal parts are now not being impacted by that cut. So this is very fancy for explaining items inside an enclosure. Next, I'm going to go ahead and talk about the hole wizard. So as I drop in another assembly feature, this time around the hole wizard, maybe zoom in a little bit, as I accept this countersink, I can see the hole going through both parts, but if I go to this part here, I can see that there is no hole in any of the four corners. Likewise, if I go into this component here, no hole here either. So instead, I'm going to go ahead and undo that hole wizard. Now I'm going to go ahead and try a whole series. So insert assembly features, whole series. Here I could add additional points for additional locations, but I'm going to go ahead and create a new hole. This is going to be here again a countersink for a number 4. If I had a middle part, I could specify based on the starting hole, like a screw clearance. And then my last part is going to be a tap hole, tapping into that component there. So when I hit OK, I get the same type of hole. Now, if I go into this part, though, I can see that that hole has propagated back to the part. I can see it's an external reference. And in the 07, they added the quick reference guide. So here I can see that reference is present, that symbol there. Very valuable document if you haven't checked it out yet. I'm going to go ahead and take a look at the housing. That should have the tap in it. As I open this part here, I can see the tap with the reference. So if I update the assembly, these items will also be changed. I'm going to go ahead and close this here. Okay, the next assembly I'm going to open is called Conveyor Mess. And the reason I named it that is they didn't plan this assembly out very well. As this tree opens up, we'll see that there's a bunch of parts in a row without any real structure. We have one sub-assembly, but as I zip down the tree here, you can see there's nothing but parts as far as the eye can see. If I take a look at how many components are in this top level, I can do this through the assembly statistics. Okay, right here, total number of top level components, 341. That is, SOLIDWORKS needs to solve the degrees of freedom for 341 components. In other words, it needs to solve for 826 mates, limiting the degrees of freedom of 341 components at the top level. I did mention that we can form sub-assemblies if it wasn't planned out well. So as we take a look at the front view, I can zoom into the side over here, and I'm going to go ahead and collect these parts here, and then I'm going to go ahead and form a new sub-assembly. So as I find them in the tree, right click, specify form new sub-assembly here. I'll accept the defaults, and now I'm going to get a sub-assembly in the tree. So now if I open this sub-assembly, I can see all of the components as well as all of their mates. I also mentioned that if we want to move components into or out of sub-assemblies, we can do that as well. So maybe I want to move a component like, I don't know, this pivot cylinder into this sub-assembly here. When I do this, I'm probably going to break some mates, so bear with me. I'm going to go ahead and move it. And as I move it, I'm probably going to get an error box, or you're going to get over definition, as in this situation here. So what I did, though, essentially is I took this cylinder and I put it in this sub-assembly. So as I travel down the tree, here's that cylinder. If I were to open that sub-assembly, likewise, there's that cylinder. I also mentioned that we can demote the parts, so I'll just take that same cylinder and I'll drag it into the top level. I also mentioned that if you don't want this to be a sub-assembly, we can dissolve it. So to do that, I'll right-click on this assembly and specify dissolve sub-assembly. That pulls all of those components into the top level here, and once I do that, I get a long tree because all those parts are now at the top level. And to make this an absolutely horrible assembly, I'll go ahead and do that to the first sub-assembly and dissolve that as well. Okay, so there is everything at the top level, no sub-assembly structure whatsoever. Now, if we take a look at an example using the sub-assemblies, we're going to show the differences here. Basically, the difference is if I go to the assembly statistics, okay, I've got the same number of components, but the difference is the number of top-level mates and the number of top-level components. I've only got 11 components to solve degrees of freedoms for, controlling with 35 mates. This is going to run exponentially better than the other one. For reordering the structure here, you see I've got a bunch of sub-assemblies. If I try moving this conveyor at the beginning of the tree to sort of alphanumerically, you'll notice that it wants to demote this component into that subassembly. If I hold the Alt key on the keyboard, you'll notice that that icon changes. So now I can reorder subassemblies without fear of demoting them into the subassembly that you're dragging it above or onto. And with that, I'll go ahead and close this. And on to some mate tips and tricks. Hopefully these items will help you put together your assemblies a lot quicker. The multi-mate mode is a feature that was introduced in SOLIDWORKS 2007, and that basically allows us to specify one common reference and then mate the selected components to it in one step. The Smart Mate mode is when we're in the assembly. If we hold the Alt key on the keyboard, we start dragging a component from a face, and based on that selection, whatever face you then move over to, SOLIDWORKS will try to determine the best possible mate between those two entities. In addition to that, it will also give you a pop-up toolbar that will allow you to specify the mate that you actually want. From tiled windows in SOLIDWORKS, we can drag and drop components into an assembly, and based on the faces and or edges that we drag with, these parts will also snap into positions similar to the Smart Mate mode. When building a component, if we know exactly how that component is supposed to be used in an assembly, we can go ahead and specify references at that part for mates when we get to the assembly. That way when we drag and drop that part, it will go ahead and snap into position based on the mate references that were put together at the part. We also have some advanced mate types. The width mate allows us to specify center between a set of faces between two parts. This comes in handy if the original parts were not planned out with planes running through the middle, as I outlined in my design planning webcast. It is a good practice to keep in mind symmetry as well as placement of planes at the part level. The width mate works by being able to specify two sets of faces on each item, and then SOLIDWORKS will determine the middle for you. The next advanced mate type, limit distance or limit angle, similar to the standard mate of distance and angle, except for the fact that it gives you the ability to specify a total range for that distance. For example, if you take a shock and you know that the shock, taking its mounting structure to the body of the shock, maybe we have a known distance of 1 inch at the shortest portion of its travel, and the maximum distance on its travel would be 15 inches. Well, we can set it up that way inside SOLIDWORKS. That way, when we move that component, it'll behave just like the real deal. Limit angle works the same way. Maybe you're mating a cabinet door, and when you close the cabinet door, that angle would be 0. Open it all the way up, it might be 90 degrees. So we have the ability to control that as well, just like the shock. We also have a gear mate that allows us to specify a ratio between a set of cylinders. The symmetric mate allows us to specify a plane to locate parts symmetrically about that plane in relation to one another. We have a cam mate that allows us to specify a follower and a cam surface and make sure that those surfaces never stop touching. New in SOLIDWORKS 2007, they added the rack and pinion mate, and this allows us to take rotary motion and generate linear motion or vice versa. And then finally, we have the ability on any component to right-click to view the mates to help us understand that mating structure, so that way we can quickly determine issues as errors pop up. So I'll go ahead and open the multi-mate assembly. And to use the multi-mate mode, it's this toggle here. And when I'm in here, common reference, I can pick a common reference. Then I go ahead and click on the components I want to mate to it. And then I'll pick up my next component. It's flipped the wrong way, so I have the ability to flip the alignment. And then I'll go on to my next component. Here again, wrong alignment. I can flip that alignment, pick the next part, flip alignment if necessary, and then pick up the last component and then accept that. Now each one of these components has a concentric mate. As I pull these out to kind of align them how they may go in the assembly, I can go in and finish with my additional mates. And with that, I'll go ahead and close this one. Alright, next I'll go ahead and open an assembly to show smart mates and also from drag and drop. So as I grab these items here, I'll go ahead and tile them. And then what I want to do is point out that this part here has a clocking feature as well as it has a bolt pattern. And if you take a look at this housing, it too has a bolt pattern. So if I click on this back edge and drag it into the assembly, you can see that that part snaps into position and the bolt pattern lines up. If I hit the tab key on the keyboard without letting go, I can specify where that clocking lug is supposed to be. When I let go, it's going to go ahead and add 3 mates for me. It's going to add a concentric, between the outside and one of the bolt holes, and then a coincident between those 2 faces. So that's a handy one if you have components just like that. Next, I'll go ahead and demonstrate the Smart Mate mode. That is, if I click and hold Alt on the keyboard, I can drag a component and snap it to a face, and it doesn't really matter which face I click on. It's going to try to adjust to wherever that face happens to be. So if I come over here, I can drag and drop it onto that face. Here's the pop-up dialog I was talking about. I want a concentric there. I can specify OK on that. And maybe I want to go ahead and add a coincident between this flat face here. So I'll hold the Alt key. Watch your cursor feedback for this. So there I have the feedback that's telling me it's going to go ahead and add a coincident. As I do that, I get to confirm coincident. Likewise, another smart mate is if we have a situation like this commonly found on fasteners, if I hold the Alt key and grab on the inside edge of that shoulder and then snap it to something like this, you'll notice that it's concentric and coincident. I need to hit the tab button to flip the alignment. So now when I drop that component, I can see that this item here has a couple different mates, all with one smart mate motion. And finally, I'll do the same thing with this here. I'll go ahead and grab the Alt, start dragging this item, and I want to make that concentric there. And then maybe I'll drag this flat face over to here and mate that coincident there. Okay, the last item I wanted to show here with this particular item is mate references. Now you may or may not be aware that the toolbox already has some mate references ready to go, and it looks like I need to add in my toolbox. So I'll go to Tools, Add-ins, and turn that stuff on. Okay, now when I drag and drop a fastener from the toolbox, I'm going to go ahead and drag and drop a machine screw to go ahead and fit in there. Now as I hit the tab button, you'll notice that this item wants to snap into place. And the reason for that, it has mate references. So if I open this part, I can show you that this in fact has a mate references folder. And this is how they specified the mate reference so it snaps into place. Now I'm going to go ahead and show how to do that as well. So to capture or demonstrate how to make mate references, I'll open this mate reference assembly. And you might recognize these toys. They're just like Legos except that they're magnetic, which makes them stick together. For this, I'll go ahead and insert a mate reference. That's from reference geometry, mate reference. And from here I could specify that that face there always wants to be concentric and that this face here always wants to be a coincident. But I'm not going to capture it that way. Since these are magnetic and these spheres are metal, it means that it will stick to these or to itself. So to accomplish this, I'll use a standard mate and go ahead and make this concentric, and then I'll do a coincident between this face and the other one. As I do a select other, I want to mention the select other. This list you can pretty much ignore it. What I want you to take a look at is the mouse icon. The right mouse button is a pair of eyeglasses. This allows us to hide faces out of the way, so that way we can zoom in on the face that we want, which is this one here. I'll go ahead and click on that. Now I can do a coincident there. I'll do the same thing on the opposite side. Do a concentric there, and then do a coincident between there, select other, and then pick up that face there, another coincident. Now that I have this as it would snap together to itself, I'll edit this part and then I'll go in to do a mate reference, and now I can capture these references, those two there. Do the same thing with the bottom two. Okay, you'll notice as I do that I get a mate reference folder. It's showing me how it's going to try to snap in. So as I edit the assembly now, I'll go ahead and delete these items because I no longer need them. And then I'll go ahead and mate my second items. This to there, concentric. Likewise this to select other. Hide that face out of the way, grab that one, concentric. Okay, now I'll go ahead and edit this part one last time and capture two more references. So I'll go into mate reference, capture that mate reference there, and then one more on the other side. I'll edit the assembly and then edit the sphere and do a mate reference capture on it as well. That one concentric over there, edit the assembly, and I got to do the same thing to the other instance of the same sphere. So I'll edit part here, do a recent command, and mate reference capture, specify that one there. Now when I edit the assembly, this is where it gets fun. Okay, I'll go ahead and open one of these parts, and then I'll open one more, which is going to be this part here. Now I'll go ahead and tile these vertically, and I'll hide the trees out of the way to kind of make this look a little bit better. So now as I zoom in on this one here, okay, if I drag and drop one of these segments in, it's going to snap to that side of the sphere. Or if I drag it in on this side, it'll snap to this side of the sphere. Likewise, if I drag a sphere in, it's going to go ahead and snap to the end there. Or if I drag over here, okay, it's going to snap right into place. Now, if I grab another one of these segments, I also mentioned that maybe you want to put two of these segments together. Well, I can do that. Okay, it'll snap to that side there. I could do that again. So basically, I ran through all the scenarios, manually mating them up front, so that way I could expand its functionality as I used it later on. And as I do that on the opposite side, we can see that this works in both scenarios. So as I expand this, you can see that just by dragging and dropping with those mate references, I was able to produce this many mates. Okay, because remember I deleted all those other items. So there's how to make your own mate references. Alright, so let's show some advanced mates. As I go to open this next file, okay, I mentioned in advanced mate, we do have a mate that allows us to center things. It's called the width mate. So to do this, I'll go ahead and grab my width selection, which is going to be a set of faces, this face, and then the opposite side on the other part. And then my tab selection, I'll go ahead and grab the outside face here using my select other. And based on the two sets of faces, SOLIDWORKS will determine the center for me. Next, if I take a look at this item, I can see that it has degrees of freedom to hinge. So I want to control how much that angle is. So under my advanced mates again, I can specify an angle mate, and I can pick these two faces here, and I want to specify inside, and I want the minimum angle to be 0 or parallel and the maximum angle to be 90. Okay, if we take a look at the front view for this, if I try moving this item, I can move it all the way down till it stops where these are parallel, or if I move it all the way up, it stops at perpendicular, even if I try pulling past. I'll go ahead and bring it in somewhere like here. Now, I want to give a demonstration of the limit distance. And in this scenario here, I have a piston. So I open this assembly. This item is free to float. Now, when talking about sub-assemblies, I did mention that subassemblies are treated like components, wherein SOLIDWORKS does not try to determine the degrees of freedom for those subassemblies. It just leaves everything locked in space. So as I go ahead and set this thing to resolved, I'm going to get an error here. Okay, until I try moving these items. Okay, now it's going to go ahead and be fixed there, even though I have a limit angle. So I'm going to go ahead and delete that limit angle. Well, if I wanted to use that angle to control this, I could make this subassembly here flexible. Okay, that would allow me to have degrees of freedom of this subassembly brought into the top level. So now if I move this, I can go 0 degrees up to 90 degrees and back. Okay, so there's that one. I'll go ahead and delete this angle here, and I want to control it strictly from the piston. So if I go to the piston, okay, if I move this, if I pull it too far out, it's going to detach, or if I push it too far in, it's going to go inside the other body. So instead, I'll go ahead and do a limit distance. That's the advanced mates distance here. I'm going to pick that face, and then likewise the same face on this thing. And my minimum value is going to be 1425, and my maximum I want 10 inches. The reason it wouldn't let me change the values, the current position is 1 inch, so I'll make that 2 inches. Now I can change this to 1.425. Now if I try moving this item, okay, it'll pull out to 10 inches or go back to 1.4 and some change. Okay, now when I go back to the assembly, I can move this item, and based on the piston length or travel, will determine how this thing is positioned. Next, maybe we want to see how items are mated together. So if I go back into this piston here, if I right click on a component, I can show the mates or view the mates, and this helps me understand what's going on with this part here, the pivot cylinder. Okay, I've got a fixed item here, a concentric over here, a limit distance, the one I just threw in, and a parallel. The other way to view this is if you click on a component, you can go to the property manager, and this lists all the mates that belong to that component. If you click on two components under property manager, it shows all the mates between those two components. And with that, we'll go ahead and go back into the assembly. Once again, based on that limit, I can move this thing just like that. Now back on to the next topic. Component patterns. Well, why should we use component patterns? Like most things, if we can make our job easier, it's a good idea, especially when it's more accurate that way. What I mean by all of this is if we take an item that we know is correct and we reuse it over and over again, then we only had to make sure it was correct the first time. Well, consequently, if it's easier for us, it's also easier for the computer, because likewise the computer calculates the data set once, and then when we request a component pattern, it just takes that same data set and copies it across the following parameters that we ask for. The reason this is easier for the computer is these copied components will be based on the very first item, which was the seed item that we made the pattern from. These component patterns can be driven from a feature from a part inside that assembly, or we can specify a component pattern right there in the assembly, be it a circular or a linear pattern, not related to any one part. In addition to this, pattern instances can be skipped or suppressed to make irregular patterns. Component pattern instances can also be configured. So if you have multiple configurations of your seed components, then throughout the instances you can go into any one of them and switch which configuration that particular pattern location is pulling in. Component patterns can also be dissolved if necessary, and what that will do is similar to dissolving a subassembly in the fact that it'll bring all those components into the top level assembly. Plus we have the ability to mirror components, and when we're mirroring a components we have two different options. We can do a positional copy, which simply mirrors the part positionally only using the same side of the part in the other location. or we can have an opposite hand copy of that part that is derived from the original. So we can have a true right hand, left hand type of situation where the part is not only flipped positionally but also geometrically. So to show component patterns, I'll go ahead and open another assembly. And from this assembly, let's go ahead and take a look at this very first part, the keypad. And as I roll back the tree here, I can see that the linear pattern here is filling all areas. And then they took a cut to clean up in a few areas to make room for a larger button. So having said that, let's go ahead and take a look at the button. And there is a large configuration at this button. So as I take a look here, here's the larger button. So now I'm going to go ahead and insert a component pattern. So a component pattern here, I can do a local linear pattern or a local circular pattern. What I mean by local is the fact that it's only being driven in the assembly, not based on any other component or anything else. So first off, I'll do this linear pattern. I'll pick that edge and that edge for my directions, and the component pattern is this button here. I'll go ahead and flip direction on these and specify multiples in both directions. Okay, so that is an independent local pattern. And the other component pattern that we can do would be based on a feature. So I'll do feature driven. Components of pattern is going to be this one here, and the driving feature is that item there. Now as I do that, I see that multiple areas where we had room for the larger buttons, it's filling in 2 buttons in each one of those areas. Well, I'm going to go ahead and skip some of these instances, like these here on top. Okay, and after I accept this, I can then convert these 4 buttons here to the larger buttons. So I'll accept that there, and then pick with Control Select all 4 of these items, and then do a component properties on this. And now I can specify to use the name configuration. Notice the default is to use the same configuration as the pattern seed component. Instead, we're overriding that with the large configuration. When I hit OK on that, you can see that it places in 4 of the larger buttons. Now we'll talk about mirroring a component. So I'll go and insert mirror components, and I'm going to go ahead and pick up the face I want to mirror about. And you'll notice that there's 2 options. So the component I want to pattern is this one here, and with the current selection, this gray box, it's going to copy that instance on both sides. It's not going to modify the part, it's just going to move a copy of it over there. So as I click OK on that, I get an exact copy of that part. Okay, it hasn't been mirrored at all, it's just been copied positionally. Now I'll go ahead and suppress this item here, and then we'll show what it looks like when we have an opposite hand of that part. So I'll go into Insert Mirror Components again. This time around, picking the same face to mirror about, picking the same component to mirror, only specifying by clicking here that that mirror component has a right and left hand version. As I accept that, and here we have a mirror opposite of that first component. So if I open this, I can take a look at what it looks like, and here's what I was talking about being derived. It is being driven based on that keypad part. And with that, go back into the slideshow. For the greatest efficiency use of assemblies, we can ask SOLIDWORKS to give us information based on our assemblies, in addition to, gee, will these parts go together and how will it look? Well, we have the option to do mass properties. That takes the volume of each part times a density, which is based on the material, and calculates how much this part would end up weighing. Now, when doing this at the assembly level, this is assuming, much like the part level, that the accurate material has been assigned. So for the assembly level, an accurate material has been assigned to every single component in that assembly. Keep in mind that this number is still an approximation since your models are going to be nominally perfect. It also assumes pure material with no inclusions or impurities throughout the material. In addition to this, we can ask SOLIDWORKS statically, do these components interfere with one another? And if so, where? Or we can check for interference in a moving assembly through the move component with collision detection, by where we can take the component and move it, and throughout its entire range of motion, if it collides with another component, SOLIDWORKS will flag us and alert us to where they're colliding as well. In addition to this, a more valuable tool, maybe we want to find out how close things get to one another. This is move components with dynamic clearance. That will tell us the closest distance based on the components throughout their range of motion. So that way we can tell if we've built in enough tolerance to each part to make sure that this thing is going to fit together in all cases without colliding or without interfering. With the age of 3D modeling, exploded views of assemblies has now become commonplace, and they have added invaluable clarity for assembly drawings. It used to be only a technical illustrator had the ability to create exploded assembly views. Well, now everybody can do it. In addition to this, we can use physical dynamics to find out how parts will interact with one another based on their mates. So when you grab one component based on the degrees of freedom of all the components in the chain, that part will interact. And finally, simulation. We have the ability to apply motors to different components throughout the assembly, and this can be used for analysis or for animations. Okay, so to get additional information from an assembly, I'm going to go ahead and open this here. And the first thing I want to do is find out how much this thing weighs. So from the tools pull down, I can go to mass properties. And the data based on a density of 0.036 says that my entire assembly weighs 0.32 pounds. Now that seems a little bit low for my specific assembly. If I close this out, I may want to spot check some parts, maybe all of them, unless I made them and I know that each one has a material. And as I find here, this one doesn't have a material applied, so I can go ahead and add a material. And then based on that, I can go ahead and check my mass again. And at 0.036 before, now I'm over a pound. So chances are a lot of these components don't have any materials applied, so I'll need to run through and do that. Okay. In addition to that, maybe I want to find out if there are any interferences in this assembly. So from the tools pull down, I can ask for interference detection. Now from here, I have to hit calculate for SOLIDWORKS to run the calculation on the assembly. And based on that, it finds an interference. In fact, it finds 3 different interferences. Okay, so as I take a look at some of the options here, line-to-line design has always been a problem in industry, and as much as it was an issue in 2D drawing days, is still a big issue with 3D drawing days. After all, the number one reason it's a problem is tolerance. So in modeling, you also want to avoid line-to-line design, and interference detection has an option here to treat coincidences as interferences. So you can turn that on and recalculate the interference. In addition to this, you could have SOLIDWORKS treat subassemblies as components. Now what that's going to do for you is, if that thing's off, any subassembly that's in there, SOLIDWORKS is calculating each component to itself and other components around it if there's any interferences. Doing this on a large assembly is going to take a while. So what you may want to do instead is open the subassemblies, run interference detection on those subassemblies. After you've cleared up those interferences, then go back in and tell SOLIDWORKS to ignore those subassemblies. That's what treat subassemblies as components is going to do for you. Therefore, it'll calculate only the top-level parts and top-level subassembly components, see if those are interfering. In addition to this, we could include multi-body part interferences. That is, if you have weldments or things of this nature, it will go back into the parts toggle. This will force SOLIDWORKS to go inside each part, check each body inside that part to see if they interfere. In addition to this, we could have the interfering parts transparent. If I uncheck that, then it will just give me an outline of those interferences. So making these interfering parts transparent kind of helps the clarity. And speaking of clarity, the non-interfering parts, we could have the non-interfering parts as hidden, as transparent. Using current will allow them to stay shaded, or wireframe will just give us an outline of the components that are not even involved in the issue going on at the current time. So as I look at these three interferences, it looks like it's this area, which means I need to take a closer look at a mate perhaps that belongs to this part. And as I hover on this, it highlights the edges in red, and we can see that the boundaries of this part are in fact embedded into this bracket here. And kind of a best practice, I recommend everybody uses shaded with edges. When you do this, not only does it add clarity to your design, but as we take a look at these parts, I can see that the black line here stops. In other words, I don't have a black line down here, so it's kind of a visual cue that maybe there's an interference here, so there's another good reason to use it. And as I dive into my mates for this particular part here, or this sub-assembly, I can see it's got a concentric, a parallel, and a distance. So if I edit the feature on that distance there and maybe take a look at the front view, I can see that I've got a 40 thou distance being applied in the wrong direction. So if I flip the dimension, now I'm going to push this part out. So now I believe I've eliminated that interference. So to double check it, I can go back in and ask SOLIDWORKS to run interference detection and specify calculate. And here it says no interferences were found. Now, there may be some interferences that you want to ignore. Okay, these will be situations where you have tapped holes. The hole wizard creates holes at the minor diameter of the thread, and the toolbox fasteners are generated at the major diameter of the threads. So you will have that interference where those threads would otherwise be. And from that, let's go ahead and ask SOLIDWORKS if this thing is going to collide in a dynamic state. So as I hit OK on this, if I move this item, I can see it is in fact a moving assembly. So from the move components, I can ask SOLIDWORKS for collision detection, and I can specify which components to check between. All components, since this is a small assembly, that's probably okay. If I had a large assembly, I may want to isolate only the components that I'm concerned with. The larger assembly you try to do this on, the more crunching power that the computer has to do. So I recommend saving before doing this. We don't like it when SOLIDWORKS decides to take a break on us. So I'm going to go ahead and run it on all components, and as I move this and it hits something, okay, I'm going to get a sound to be alerted that there's something going on, and as I take a closer look, I can see that these faces here are the ones that are interfering, or colliding rather, about to interfere. If I reverse the other direction, I can see likewise that these faces are in fact colliding. So I'll need to fix that collision. So to do that, I'll edit each part and add a chamfer to both sides, and do the same thing to the top one here. Okay, so now if I do move component with collision detection on all components, having it stop at collision, when I move this thing around, it looks like I've taken care of all the colliding items by adding a chamfer to eliminate that pinch point. However, I'm not sure if all of my tolerances are correct, so to find out how close these items get, dynamic clearance down here, for this particular item I need to specify which components to check clearance from. So I'm going to check between these two items here, since I kind of know where this pinch point actually is. As I resume the drag and move this, I get this dimension appearing up here, and it's showing me that these items come as close as, looks like about 3 thou. Now when I'm running through the range of motion here, if you look in this dynamic clearance box, it's telling me the current position and the minimum, so 3 thou. Chances are this is going to wind up rubbing or hitting when we put these together. So with that, I'll go ahead and take us into the next part. So I'll open the next part, or next assembly rather. Okay, these parts have been mated together with degrees of freedom based on their mates. Now, what I may want to do is drag this component, and provided that the other components that it's attached to have degrees of freedom, have the movement of the first part cause a movement in each part in succession. So in order to do this with the move components, I have the option for physical dynamics. Now when I click on a component and start pulling on it, if those other components can move, they all move until I try running into another part. Now as I rotate around, basically when this item comes into contact with another part, okay, it's actually doing collision detection. And let me swing this thing around to kind of show that. Based on that collision, this part is going to roll off the other part to avoid an interference. Okay, so in order for this physical dynamics to work, you need to go through, run interference detection, because if you have an interference, this will stop right away. And then you run collision detection through the full range of motion, make sure everything is able to move, and then finally you can do the physical dynamics and see how this item might operate in the real world. Okay, so from there, I'm going to go ahead and demonstrate an exploded view. Okay, when I click on the explode view item, I get a yellow box. It pays to read all these dialogues that SOLIDWORKS has prepared for you. And in this scenario here, it says select a component and then drag a manipulator handle to create an exploded step. So as I click on a component, I get the triad. And now if I click on one of the triad handles, it's going to pull it along that axis. Now in this scenario here, it's clearly not lined up with my component. So in order to make this look more professional, I may want to right click on my triad and say align with the component's origin. Now when I click on an axis, this axis is going to be lined up with that part. So if this was the exact view I was trying to pull into my drawing, I would do something like that there. After I've moved that component and dropped it, I get this blue arrow, and this is basically a fine-tune arrow. I can fine-tune the position, either bringing it closer or further away till I find where I want it exactly. Once I click in the background, I complete that explode step. So maybe I'll click on multiple components and then align again, maybe with this here, and then pull that straight up, or actually straight out. Okay, I'll go ahead and complete that step there, and then I'll do one more, taking these three components and aligning to selection again. And I'll go ahead and pull it in that direction there. Now, once I've completed my explode view, I may want to add reference lines to show how this item is put together. So with my exploded line sketch tool, it takes me into the route line command. And basically, this is a special type of tool for 3D sketching that allows me to click on cylindrical faces by which SOLIDWORKS will pick up the axes of that face. And now this arrow indicates it'll be going down. I'll go ahead and flip the arrow so it's going up. And when I click on this cylindrical face, it'll go ahead and route a line over to that cylinder. Now the option along X, Y, and Z is going to force that sketch to go along X, Y, and Z. So if I wanted something that wasn't lined up, I could uncheck that, and it's going to give me a straight line distance between the two. So I'll connect those there. I'll do another one from this hole here, reverse the arrow, come out to this boss. And in scenarios like this where it looks like that line's going through the other item, you can drag this. When you see the double arrow, you click on it, you're able to pull that out. Looks like it's in a tight quarter. Let me uncheck along X, Y, Z. There you go. That helped me out a little bit. Now I can drag this something like there to give me something that's more legible. So I'll accept that, and then my last explode line, I'll go from here to there. Okay, now when I take a look at an isometric view, I get an idea of what this is going to look like on the drawing. And with that, we'll go ahead and show the next assembly. And the next assembly is a set of bevel gears. So let me find it here, simulation. Okay, with these bevel gears, if I were to do a move component on them with collision detection, okay, I can see that they collide. And if I did physical dynamics on it, since this item has degrees of freedom as well as does this one, when it collides with the other component, it'll push it out of the way. So as I zoom in, I can actually witness the backlash as I switch directions. Okay, the reason I'm going through these steps is it's critical that these assembly components do not collide at an interference. In other words, they can go through their full range of motion, that although they might collide, they never interfere based on degrees of freedom. So what I'm setting this up for is the simulation. Okay, with this simulation I have the option to add a linear motor, a rotary motor, or a linear spring, or gravity. And in this scenario here, I'll go ahead and specify a rotary motor. And in this here, I'm going to grab on this shaft to indicate the direction that I want this motor to spin. I do have the option to flip the direction, whether it's spinning counterclockwise or clockwise. I can set the velocity with this ramp chart or numerically. Probably more accurate doing it numerically. So maybe I want this thing to spin 360 degrees per second. Okay, and as I apply that, you'll notice that we get a simulation folder in the tree, keeping track of all my motors that I might have applied here. So after I've added that simulation, I then have to calculate that simulation in order to see what it'll look like. So as I calculate the simulation, I can now see how the parts will interact based on my motor. Once it's done calculating, or I've seen enough, I can hit escape, and that then saves that calculation. So if I ever want to recall it for like a replay, I can specify a replay, and right now I have it looped. It's going twice as fast. I can go ahead and slow it down. So this is showing you that every 1 second it's spinning 360 degrees. So aside from that, this can be saved out as an AVI provided you have Animator added in. So to demonstrate that, I'll go to Tools, Add-ins, and through SOLIDWORKS Animator, with that turned on, now when I replay that simulation, this record button is now available. I can save it as an AVI. If you go into your animation tab and you want to reuse that simulation, you go into your animation wizard, by which you can now specify a physical simulation, and that's going to be the one that I went ahead and did. The duration is going to be exactly as long as I calculated it. So as I finish, when I hit play, I'm going to see that very same animation. And with that, I'll show gravity, one last item, and I'm going to go ahead and copy this part straight up, and to make sure that it stays in line with this, I'll go ahead and take a look at the front, maybe the side. Okay, basically when I drop this thing, I want it to collide with the gears and then roll off the edge. So I'll do something like that there. Okay, so the next simulation I'll apply here is going to be gravity, and I'm going to specify this for the direction, and I want it going down. So now when I calculate this, we're going to see the rotary motor and the gravity happening. So I'll go ahead and hit escape since that's fairly short. Being able to see the gravity, I'll go ahead and replay that simulation, and I'll slow it down to kind of see what happens when this thing collides with the bevel gear. Okay, so as it falls, you can see it rolls off the edge as it would if you physically dropped it on it. And you can see here in my simulation folder I have that rotary motor and gravity both being applied. And with that, we'll go back to the slideshow. Simplified configurations. In order to give your computer a break, you might want to think about incorporating a simplified configuration in complex parts by eliminating excessive details and things that are not necessary to manufacture the part. There is an automatic way to do this. It's included with SOLIDWORKS Office in the Utilities add-in. It's called Simplify, and based on a simplification factor that you request, SOLIDWORKS will go through and calculate all the heavy features on each component, and in doing so we can ask it to suppress those features as well as make a configuration with those suppressed features called Simplified, and make sure that if you have a subassembly, all the components will have a simplified configuration. That subassembly will also have a configuration named Simplified, all the way up to the top level assembly that also has a simplified configuration, and everything is lined up. So all you need to do is double click on Simplify, and you have your simplified light version that you can use for day in, day out work. Another item, in addition to eliminating features, you can use textures in place of patterns for parts that are made out of perforated material and other items similar to that. And with that, we'll go ahead and demonstrate some more inside of SOLIDWORKS. So to show this simplification, I'll go ahead and open this assembly here. And so first thing I need to do is add in my utilities, and then from the utilities pull down, I'll have the ability to ask for an automatic simplification, and I can ask it to simplify all and specify simplification factor. Maybe I'll do 5, and maybe I want to ignore features that might affect the assembly mates, and with that I can specify fine now. It's going to run through and try to simplify my assembly, make it 5 times simpler. Now it found all these items that are heavy, so if I had all these things suppressed, it'll be 5 times simpler. If I hit suppress, that's what I'll get. Now the power comes in this derived configurations. Okay, if I do that and hit suppress all, now it's going to create a configuration at each part with those items suppressed, and also at this assembly level with those items suppressed. So here my items are, my parts in their simplified glory. Okay, here's my simplified derived configuration. Therefore, anything that happens to the default happens to the child. So if I double click on default, I get my fully loaded parts with all their chamfers and all their fillets. I double click on simplify, and it makes it 5 times simpler. So if I take a look at one of these parts, I can see that this part has a simplified configuration. Apparently it didn't find anything to simplify on that one. So I'll go ahead and open another part, maybe this one here. Okay, on this I have a simplified configuration and a default. So that's going to save you some time. And the reason you want to have SOLIDWORKS do this for you is trying to make all these configurations line up with one another, especially of several levels deep of subassemblies, can be quite a lot of work. So with that, we'll go into the next item. Lastly, I just want to run through some quick best practices. Use subassemblies whenever possible. This eliminates the need for the computer to crunch those degrees of freedoms or the mates. Use layout sketches or skeleton parts as well. With this, we have the ability to mate to sketch entities and parts. Even if those parts aren't going to wind up in the assembly, just use them as positional parts to locate items. This is especially useful if you're going to be utilizing configurations, because if you're suppressing items in certain configurations, that may impact the mates. So you want to keep all this stuff in mind. And if at all possible, plan parts with their planes for use for mating when you get to the assembly. Same thing applies when you're going to utilize configurations. As long as you're using part planes that are at the beginning of the part tree, then you're probably not going to run into a situation where those planes will be suppressed. If you are going to be utilizing configurations, throw a design table in there. It's a good way to figure out what's going on with your assembly and what the differences are between the configurations. Another good practice is to resolve all mate conflicts and feature errors as they come up. And finally, if you don't have to model parts, don't, especially if you're not manufacturing. Go to 3dcontentcentral.com. This is also available in the SOLIDWORKS task pane. And with that, I'll go ahead and take us in to show layout sketches. Alright, we're running out of time, so unfortunately I only have time for one last example. And here I'm going to show the use of layout sketches. So here I have a layout sketch to position these conveyor frames. So I'm going to go ahead and do a mate to this sketch entity here and this face here. Maybe a coincidence. And then likewise there. Use my select other, grab that there. Okay, all 3 of these items are mated to the sketch. So if I manipulate the sketch dimensions, I'm going to be moving these items around. So as I crank this thing up and hit rebuild, I'm going to see that thing move. Okay, so if you have a 2D layout, maybe from AutoCAD or something else, that you want to position your equipment, go ahead and use it, mate to those sketch entities, and then you can manipulate them with actual sketch dimensions. And that's all we have time for today. As always, it's been fun. Thank you for joining us for another DDI webcast. I hope to see you next time, and don't forget to check out our podcast and sign up for the webcast archives. There was a lot in this particular webcast, so you might want to watch it again. Go sign up for a password, and you'll be able to download it shortly after we post it. Until next time, I'm your host, Joseph Richter. Take care, everybody.
Psst. Hey you. You still here? I just wanted to thank you for making your way to DDI's Customer Center and requesting a password, because this is actually exclusive content that was not available in the live webcast itself. And basically, for the reason that I'm presenting it is we ran out of time, and I still wanted to go through that last item, the design tables. So as I open this part here, it's basically a cabinet door frame, and as I double click here, I've got two dimensions, height and width, and these are being driven in the design table. As I edit the table, okay, here's the table, and you can see that the name of the configuration is actually being based by the width and the height. So 11 1/4 here by 22 1/4 here, and you can see it matches all the way down. And as I click over to the insert, got the same thing going on. Okay, here's my height and my width dimension. And as I take a look at the table, you can see that I have the width and the height. For this door, it requires that insert size. Then finally at the assembly, okay, the different configurations are pulling in different configs of the parts. So as I double click on this one here, it's pulling in the 14 1/4 config for both the frame and the insert. And some of these items are not even using the insert at all. So as I look at this design table here, okay, it's really easy for me to see exactly what's going on with this assembly, having everything match. So anytime you're going to use configurations in an assembly, it pays to go ahead and drop it in a design table, and then without double clicking on each configuration, you can see what's going on. I can see which configuration of the door frame is being pulled in for that config, likewise the insert, and finally whether or not that insert is actually suppressed or resolved. So in this configuration here that did not require that insert, you can see that it does not display configuration name and in fact is suppressed. And to close out this bonus session, I want to revisit the U-joint. And here I want to point out the status bar. It tells me I'm editing my assembly and that my assembly is underdefined. I can also see this from visual cues in the tree. I can see that the minus symbol in each front of this components tells me that these components have degrees of freedom. Now, when looking for completeness in the design, I like to know that every part has its place and is fully locked down. Now this item here is a moving assembly, so having those minus symbols in there might not seem like a bad thing, but I will point out that that minus symbol should stick out like a sore thumb, telling you that there is something that is not locked down in your assembly. If I take a look at the quick reference guide here, these status indicators apply to both sketches and your assembly components as far as degrees of freedom. To limit this assembly, to allow it to fully rotate, I can go ahead and add an advanced mate of an angle and specify my planes, maybe the front plane between that and my male yoke. Okay, and I want my range to be 360 and my minimum to be 0. Now, looking at the setup, I'm pretty much not limiting anything, but what I am doing is I'm informing SOLIDWORKS that this male yoke is free to spin 0 to 360 degrees. And once I do that, if I take a look at the tree now, I can see that those minus symbols are gone away from the male yoke and the spider and the female yoke. These pins here probably need to be clocked, so I'll go ahead and add a parallel mate to them. And this applies to all assemblies, those with hardware. I would take the extra few minutes to add in a mate to clock them. That way you'll know next time you come to that assembly, if there is any minus symbols, it's because something's not fully locked down. So now that I've gotten rid of all my minus symbols, if I click and rotate this thing, you can see it still has its full range of motion. So the ultimate advice is take care of your assemblies and they'll take care of you. After all, nothing is efficient about having to redo work or catch errors when it's too late. So that's the ultimate efficiency in assemblies, is accuracy. Until next time, I'm your host, Joseph Richter. Thank you.